Good evening and welcome to Space Oddities. Hope you're all well on this Tuesday evening. Thank you for joining us, and we do appreciate you spending your Tuesday evenings with us. Can't believe it's a week since we were here last time, but it seems that it is. So joined this evening by the usual suspects. Hello, Michael.
Hi there.
Hello, Roger. Are you miming, or can we generally...
Hello.
Oh, that's better. Don't try that again. Keep an eye on that one. How are you, Daz?
I'm fine, thank you very much. Hope everyone's well.
Good, yes. I think I'm okay. And how's Lou over there in the States, fading into the Andromeda Galaxy as he is?
Yes, doing fine, just holding down the other side of the Earth.
Yeah.
You mean it's not?
Somebody's got to do it.
Yeah. You mean it's not flat, though?
My Earth is not flat. Your Earth, however, may vary.
Lou, you're coming and going like you're in the middle of beaming up, or beaming down.
Oh,
anyway,
no, great. Okay.
Welcome to Space Oddities. If this is your first time here, well, it's lovely to see you. We hope you'll stick around. It's been a good week here in Spain. Extremely hot, but we get through it. And on a packed program tonight, I'm going to be telling you all about the CTA Observatory. If you don't know what the CTA Observatory is, then obviously stay tuned. Lou's going to be giving us another Battle of the Bots. Michael is going to be doing Constellation of the Week this week. Daz is going to be talking about some solar storms that we've narrowly missed receiving disaster from. And there's Roger, who will, of course, be giving us the night sky and the viewers gallery. So there we are. And just a usual housekeeping stuff before we start. If you would like to support Space Oddities, you can do so in one of a bewildering number of ways. You can buy us a coffee, of course, by scanning this QR code or clicking the link that's just appeared in the chat. And that will take you to our buy us a coffee page, where you can indeed buy us as many coffees as you like, no matter how vast the quantity. You can also support us by buying your lovely Space Oddities merchandise at the Space Oddities shop, which has a variety of... why is that not working? 1 second. Oh, it's going to be one of those, is it? Okay, 1 second. There we are. So, yes, you can buy your Space Oddities t-shirts and hoodies at the Space Oddities shop at very reasonable prices for some real quality merch. And you can also make a donation directly to Space Oddities by clicking the Super Chat icon, which is the one with the $ on underneath the chat window. We also hope that you will join us on Patreon, become part of our Patreon community. That is easily reached by going to patreon.com/Space Oddities. We've got a lot of goodies for you there if you become a Patreon member for a very reasonable price every month. All the presentations that we give you every week here on Space Oddities, they're all there. We've also got all our videos from April's Moon Month, which we'll be adding to. We'll be putting lots more videos and stuff up there as well. Plus, if you join, you get a present from us, which is 2 10x8 astronomical photographs taken by two of our Space Oddities, 2 or more of our Space Oddities astrophotographers. And all you have to do when you join Patreon is to look for the chat entitled For New Members, and that'll tell you how to claim your lovely 10x8 photographs, which are ideal for framing, of course, and putting up on your wall. So there we are. And we've got lots of stuff over there. There's a chat there where you can engage with other members and all sorts of stuff. So head to patreon.com/Space Oddities and do join our Patreon community. All the money received, of course, as I always say, goes towards keeping Space Oddities going. And we would like to keep it going, and we hope you would too. So help us out to pay all our bills, of course, by becoming a member of our Patreon community. So that's it. So without further ado, let's get on. Now, firstly, there's no news this week because there weren't really that many news stories this week. One I would love to talk about, though, just give me 1 second, concerns a very interesting and enjoyable appointment. Just give me 1 second while I get this up. So many things I've got going on in front of me, but just bear with me 1 second, because this week saw the appointment of a new Astronomer Royal in the UK. And we're very pleased about this because her name is Michelle Doherty. And she might be familiar to viewers of The Sky at Night because she has appeared many times actually on The Sky at Night. And this is Michelle Doherty, who you might recognize. She's just been appointed the first female Astronomer Royal since the post of Astronomer Royal was created 350 years ago. Sir Martin Rees, who currently holds the position, is retiring, and Michelle is taking over from him. So we'd like to congratulate Michelle and wish her all the best her new position.
Can I just add, Andy, to that?
Yes, sir.
Not to be confused with the Astronomer Royal for Scotland, who is Catherine Hymans, who was appointed a few years ago. That's a separate post, I understand.
That's right. That's right. So, in fact, we have 2 Astronomer Royals in the UK, which is a bit confusing. But anyway, best of luck to Michelle. Really thrilled for her, because if you've seen her on The Sky at Night and other places, she's a fantastic astronomy communicator, and it's a position well deserved. So well done, Michelle. And there's another image I want to show you. Just give me 1 second. Taken by Europe's Mars Express this week, and this one, just give me 1 second. This one is a lovely image of Mars, and in particular, this is an image of Phobos over the Olympus Mons volcano on Mars. Oh, it's gone. I've got an error message for that. Let me just try that again. It's amazing. We were looking at this image before the show, and it worked perfectly. It's always the way, isn't it? Let's just try that again, shall we? Here we are. This is Mars's moon Phobos over Olympus Mons, which, as you probably know, is the tallest volcano in the solar.
That is a cool image.
Isn't it a cool image?
Very nice.
Taken by Europe's Mars Express orbiter. And although that volcano doesn't look like it from this angle, it's actually 3 times the height of Everest. And in surface area, it would occupy most of Spain, and
or the state of Arizona,
or the state of Arizona, if you like. Yes, and if you look around the edge of it, there are sheer cliffs, which are several miles high, vertical walls of rock several miles high. So anybody wanting to climb it is going to have a hell of an ascent on their hands. Who knows if somebody will climb that volcano one day?
Mm.
So,
but then again, like you say that those cliffs are really high.
Yeah.
But when you get to the top, the slope to the actual crater rim is very shallow.
It is. It's actually just a 5-degree slope.
Yeah.
Once you get to the top of those cliffs, it's just a 5-degree gentle stroll up to the top of the caldera.
Mm. But it does look as though there's possibly a couple of landslides that will make it easier to get up there rather than
Still a hazardous undertaking, though, Daz. Eh?
Well.
Daz has just volunteered to do it.
Exactly. I mean, you know,
money where your mouth is here, Daz.
Yeah.
So there we are. Okay, well, we're going to move on now. We'll go straight over to Roger. And Roger, of course, as always, is going to give us the night sky and the viewers gallery. So what's up in the sky, Roger?
Well, here we go for a week in August. We're currently working our way up through to the full moon at the weekend. So be warned. Although the moon at the moment is currently rising and setting quite at a low angle. So it will start to rise again through the week. Unfortunately, with the full moon, it's going to be a bit of a glaring object like it does, but what can we do? So through the week, we've got the summer triangle almost overhead, and obviously the wonderful galactic core over in the southern skies. And at the moment, we have got Saturn appearing into the evening skies now, and we have got proper astronomical darkness, which I'm assuming is now completely over the whole of the UK. So that's good. And we've got Andromeda coming up through nicely. So no doubt we'll start to see pictures of the Andromeda galaxy as well. And before sunrise, we've still got a few planets coming up through. We've got Venus and Jupiter coming up quite closely together. Uranus is in Taurus, but on the 12th through the week, you'll notice if you do notice with a clear sky over on the eastern horizon, we've got Jupiter and Venus getting closer and closer. And on the 12th, they'll be about a degree apart. So that could be quite a good photography opportunity if the weather is clear at that point on the horizon. So look out for that. And we're coming out through to the Perseids through the next week.
Oh, wow.
So,
Fantastic.
So we should probably start to see some hint of Perseids coming up at the moment. So keep an eye on that.
And there'll be no moon, right?
Well,
No,
yeah.
I think there is a moon this year, isn't there?
Yeah, I mean, if you go back to the 12th, it'll be about 80%. So it will be a bit of a hamper, but just be aware that there is an opportunity to see the.
Roger, there was a loud noise coming from your microphone. Just
Let's apologise for that, viewers, if that deafened you.
All right.
Don't know where that came from.
no.
So
Anyway.
there we are. So there we are. So we've got a little gallery provided by Lou and myself. Obviously, with the summer holidays and stuff, obviously we're not getting quite the amount of images through, but there we go. We've got some artwork here provided by Lou, and this is the Jupiter and Voyager spacecraft, and this is what he's managed to paint for us.
That is really good, Lou. Love it.
Lovely.
Oh, no, that's an image from my sea star.
Yeah, right.
Yeah, right. Yeah,
Oh, nice one, Lou.
that's lovely.
Yeah,
How long did that take you to do, Lou, out of interest?
Only about under 2 hours.
Wow,
Okay.
2 hours.
that's really
Yeah.
good.
We like that.
You're hiding your light under a bushel, Lou, obviously.
Obviously, yeah. Well, with all of the Doge firings out here, it's good to have a second career in the back pocket.
Yeah.
Yes, indeed.
Oh,
Yeah.
well done, Lou.
Well done,
Okay.
Lou. It's great.
And one of my forever taking pictures of the moon, which was a few days ago.
Oh, that's nice. It's very
Yeah.
sharp.
Yes, some good optics in that. This was a daytime shot, so I used an infrared filter to help get the contrast between the sky and the moon. And
That's lovely.
so,
You can hardly see any brush strokes in it at all. It's
no,
fantastic.
yeah, it's good, these filters on Photoshop. And then to finish it off, this one was part of a project I've been doing, the Eastern Veil Nebula, which I've been doing in various narrowband pictures. Unfortunately, I had trouble when I was doing the sulfur. The telescope was being a bit playful and decided to stop working after a while. It stopped tracking and stuff for some reason. So I've only got these. Each exposure is 10 minutes, and I only got 70 minutes in the sulfur, and only 4 pictures in the oxygen, because the forecast from the BBC, clear skies all night, and then after 1 hour it completely clouded over. But this is what I've got.
Oh, it's coming
But
up.
that's
I find it's quite quite good because you can see all the structure of the nebula there.
Yeah.
Despite that
lovely.
there's no color there, you can see all the filaments and
It's very
wisps
fine structure. isn't it?
Fantastic,
all
Roger.
there.
Yeah, that's excellent. Gosh.
There's even sort of some spread away from it as if it's been blown
Yeah.
away from the main structure.
Yeah,
Yeah, you can see it.
especially on the western side of it there. That's
Yeah.
that's incredible.
Yeah, I mean, some of it looks like wisps of gas, or they might even be galaxies. They look of a similar sort of structure.
Mm.
You
Interesting.
can, yes. So yeah. So that's a very, very brief gallery that we've got for this week, unfortunately. So
Right.
we must try better for next week.
Absolutely, absolutely. So thank you very much, Roger, as always, for the Guide to the Night Sky and the gallery. If you would like to submit your image to the gallery, and why wouldn't you, then you can email them to gallery@spaceoddities.space. And everybody who submits an image also gets their own little gallery on the Space Oddities website, which is https spaceoddities.space. And do go and have a look at our website. There's lots of interesting stuff on there, I hope. And you do get your own little gallery. So just attach your image to an email, one image per email, please, and mail it to gallery@spaceoddities.space. As we said many times before, it doesn't have to be taken with incredible equipment. It can be a mobile phone image, and we quite often receive those. And, it doesn't have to be deep sky astronomical objects. It could be a skyscape or anything remotely to do with the sky that you are willing to share with others and you'd like others to see, and get your own gallery on the website, completely free of charge. What about that? Can't say it fairer than that. So there we are. Okay, what we're going to do now is to move on and have a look at the CTA Observatory. And if you don't know what the CTA Observatory is, then you can find out all about it now. Just give me 1 second. And I hope you can see that. And let's have a look at this. So what is this all about? Well, the CTA Observatory, the CTA stands for the Cherenkhov Telescope Array, CTA for short. And this is a new observatory to reveal the extreme universe. And this is a project that involves over 40 countries coming together to create this new observatory. It's going to remain operational, hopefully well into the 2030s. And it possibly could completely transform our understanding of the most energetic phenomena in the universe. So let's have a look in a bit more detail. We need to stand back before we look at the observatory itself and talk about cosmic rays. Now, you might be familiar with what cosmic rays are. You might have heard the term. They were originally called cosmic rays because astronomers a long time ago thought they were actual rays coming from somewhere. But they're not. What they actually are is extremely energetic atomic nuclei, mainly protons, which, as you know, is one of the particles that make up the nucleus of an atom, along with neutrons. And these travel through space at nearly the speed of light. Victor Hess discovered them in 1912. They have incredibly high energies ranging from millions to billions of electron volts. Now, if you're not familiar with the term electron volts, don't worry too much. It's just a measure of the energy that these particles carry. They are affected by magnetic fields, however, so their paths can twist and turn, and it makes it very difficult to track back to exactly where they came from. And what happens is when these cosmic rays, these high energy protons mainly, hit the atmosphere, they decay into a stream of other atomic particles, or other particles, should I say. And this is what's known as a cosmic ray shower, because they literally decay into all these different other types of particles. And this occurs somewhere around 15 kilometers up in the Earth's atmosphere. The most energetic of these are gamma rays. They're the most energetic form of electromagnetic radiation. If you look at the electromagnetic spectrum, they're right over as the most intense energetic form of energy. And these typically have energy levels above 100,000 electron volts. And the CTA observatory will be able to detect gamma rays up to 300 trillion electron volts. I know that probably doesn't mean a lot, but these are extremely energetic particles. Why are they so extremely energetic? Because they are produced in the most extreme environments in the universe, including black holes, neutron stars, and supernova remnants. These cannot be seen by the human eye because they're out of our optical range of wavelengths that we can actually see. So they do require specialist equipment to detect these gamma rays. So we're talking about supernovae, these massive explosions when a star dies and blows up. These accelerate particles to nearly the speed of light, generating cosmic and gamma rays. Active galactic nuclei, so we're talking about supermassive black holes at the center of galaxies, which produce powerful jets of these particles. Neutron star collisions. When neutron stars collide, they generate unimaginably huge and titanic explosions, which again accelerate particles up to nearly the speed of light and impart an incredible amount of energy to them. So this is just a little bit about the particles themselves. So this collision between gamma rays in the atmosphere generates this shower or cascade of secondary particles. One of the particles is called the muon, and we'll come back to that. This event generates what's called Cherenkhov light. Now, the picture on the left is taken inside a nuclear reactor. And you've probably seen this before, that when you see videos or images of inside nuclear reactors, they have this characteristic blue glow. And this blue glow occurs when a charged particle travels faster than light is in that particular medium. So the medium that we're looking at in the image on the left is water, and the speed of light in water slows down dramatically. But when you get a charged particle that's actually going faster than the speed of light in that medium, then it generates a blue glow, which is known as Cherenkhov light, named, believe it or not, after Mr. Cherenkov. And the CTA telescopes are designed to capture this incredibly short flash of Cherenkov light when these gamma rays decay into this shower of other particles. Now, there's something really interesting about the muon. This is just a bit of an aside. It's a type of elementary particle similar to the electron, but about 200 times heavier. It's got a negative electric charge and it's unstable, decaying into other particles within a few microseconds. Now, the interesting thing is a muon lasts for 2.2 microseconds before it does decay into these other particles, but the journey from 15 kilometers to the ground takes 50 microseconds. We still detect muons at the ground. In other words, the muon is living a lot longer than it should. It should only last 2.2 microseconds, but we're detecting them after 50 microseconds. How can a muon last that long? Well, I'd like to introduce you, stepping on stage left, Mr. Albert Einstein. And what Einstein said is that from the point of view of the muon that's traveling at nearly the speed of light, time passes much slower. And because its time is passing much more slowly, it can last until it reaches the ground. Its decay from its own point of view takes 2.2 microseconds, but from the point of view of an observer, it persists for 50 microseconds. This is time dilation in action. This is relativity in action. And if you ever meet anybody who says that relativity is a load of nonsense, and you will meet countless people like that on social media, you can point to them and say, well, if relativity is nonsense, how come a muon lasts for 50 microseconds? So there we are. That's just a little thing about muons. The CTA is made up of two observatories, one in the northern hemisphere and one in the southern hemisphere. The northern hemisphere CTA observatory is in La Palma in Spain. This is going to host eventually 19 telescopes looking at lower energy gamma rays and extragalactic sources. The southern array is going to be in Chile in the Atacama Desert, along with all the other wonderful telescopes that we have in the Atacama Desert already. And this is going to be 99 telescopes of 3 different sizes, covering the full energy range and providing exceptional views across the galactic plane. And each observatory is going to use over 7,000 highly reflective mirror facets and more than 200,000 fast pixels per array, the individual pixels that will detect these flashes of Cherenkhov light. So that's going to be the makeup of it. And as I was putting this presentation together, I had the CTA newsletter that you can sign up for. And they've just announced that the contracts have been signed with several contractors in Chile to start building the southern CTA array. So this is really good news. In the Atacama Desert, of course, like every other observatory in the Atacama Desert, it's in a place of exceptionally clear and dry skies. In some places in the Atacama Desert, it hasn't rained for 100 years. So this is one of the, if not the driest place in the world, with the possible exception of Antarctica. And it's going to feature 14 medium-sized telescopes, 37 small-sized telescopes spread across 3 square kilometers, optimally positioned to observe the galactic center. The northern hemisphere site is going to be situated at the Roque de los Muchachos Observatory in La Palma, 2,200 meters up, and both locations chosen for their excellent skies and dry, clean air. So when these gamma rays enter the Earth's atmosphere, they create these particle showers. The CTA observatory will see these very brief flashes of Cherenkov radiation, and they're using cameras that can record up to 1 billion frames per second in order to catch these incredibly brief flashes of light. And from that, and using advanced processing techniques, they can reconstruct the original gamma rays properties, including its energy, direction, and arrival time. In its first 5 years, the observatory is going to generate 100 petabytes of data. And we mentioned this with reference to the square kilometer array, but just in case you weren't watching. So if what is a petabyte? Well, 1,000 gigabytes is a terabyte, and 1,000 terabytes is a petabyte. So over 5 years, the telescope's going to generate, again, this enormous amount of data. And that has its own challenges in acquiring the data, processing it, and networking it around the world for the benefit of astronomers. It's all going to be public domain as well, so you will be able to look at the CTA data if you would like to understand everything. Just a word about the timeline for this. Construction of it began last year. They doubled the staff last year. They got a 30 million annual funding increase from these 40 countries who are taking part in the project. 2005 to 27, the initial arrays will become operational, early science results beginning to emerge, and then in the 2030s, the full array completion and setting the foundation for possible upgrades in the future. So all of this, as I said, is going to be publicly available data. So if you'd like to study a bit more about the most energetic events in the universe, then you can have a look at the data yourself. So just as a conclusion, the global impact on this should be enormous. It's going to transform our understanding of extreme cosmic events, from supernova remnants to gamma ray bursts, providing unprecedented insights into the most energetic processes in the universe. As regards fundamental physics, it will revolutionize fundamental physics by detecting ultra-high energy gamma rays, probing dark matter, testing quantum gravity effects, and exploring physics beyond the standard model. And its sensitivity will help unveil the universe's most extreme phenomena, hopefully challenge current theories about particle interactions, cosmic rays, and space-time structure. So it really will have a fantastic impact on physics as a whole. So there we are. So that's the CTA Observatory. It's a really exciting project. Panel, got any comments about that?
When we discussed this on Astro Radio, going back many moons, Andy,
Oh, many.
many moons, I was amazed at how many of these telescopes were going to be erected.
Hmm.
But they weren't going to La Palma. They were going to somewhere else, another island in the Atlantic Ocean. I can't remember where it was now. So obviously they've changed their mind because
It might
as
have
far-
been Tenerife. Thinking about
no,
it.
it wasn't in the Canary Islands. It was but neither of us had heard where the islands were,
Oh,
or the
right.
group of islands. There's a group of islands a bit further out. But yeah, no, this is going to be amazing science.
It's going to be absolutely phenomenal because there's so much about these extremely energetic events in the universe that we don't understand at the moment. So it's going to be a really interesting time for physics, and we do stand to learn a lot from it. So in these uncertain times in the world, it's fantastic to see projects like this going forward and being funded and not cancelled.
Yeah, very nice.
So this is really good news. And as I said last week and the week before, the square kilometer array is going to revolutionize radio astronomy. The CTA is going to revolutionize gamma ray astronomy and the study of extreme events in the cosmos. So there we are. So that's the
that's fantastic. Yeah.
And
Because
viewers, if you have any questions, please don't hesitate to put them in the comments in the chat. So there we go.
because it'll be interesting if they can use these also and link them up with gravitational waves.
Well, this is another thing, and and Paul quite rightly says really interesting. It's going to be exciting as we get all the different new telescopes coming online. And absolutely, Paul, we've got this whole new generation of observatories observing across the electromagnetic spectrum and gravitational waves, of course. And it's going to be, I think the next 10 years is going to be even more of a golden age of astronomy than we're in at the moment. I don't think we've seen anything yet. It's a really exciting time. So there we are. Sorry, Daz, you're going to say something.
Sorry, I was just answering some. It's gone straight through. Don't worry. It's like a gamma ray. It's just gone straight through. In through the top and out me bottom. So sorry.
Well, I'll just say then that Andy, you spoke of the most extreme things in the universe. I would counter that. I think the most extreme things in the universe are condominium fees. It's my experience, at least.
Well, I don't live in a condominium, you see, so I wouldn't know.
Condominium. Yes. It sounds like a game, doesn't it?
Yeah. And I haven't got a mortgage anymore either, so I'm happy with that. So there we are. Okay, so yes, so that's the CTA Observatory. Any questions, please put them in the comments. And can I just say hello to everybody who's here? I haven't had a chance to say hello to all yet. So thank you, Paul, for that comment. Ian, nice to see you. Derek, good to see you as always. Hi, Melinda. Sandra's there. Sandra did say that, by the way, that as regards Olympus Mons, there's an easier way up on one side without going up the vertical cliffs. That's
they got a ski lift.
Yeah, yeah, ski lift. That's too easy, Sandra. Where's the fun in that? Where's the fun in that? So
But that one train though, like Snowdonia.
Actually, just another interesting fact about Olympus Mons is that it's actually so high and it's so how can I say the width of it is so massive that if you actually stand on the top, you can't see the Mars's horizon. You can't see the edge of the planet because it's so high up. Yeah, because you're so high up.
Yeah,
and it's such a narrow sort of like gradient that you can't actually see the sort of like the horizon of the actual planet itself. You can only see the horizon of the edge of the Olympus Mons.
I did see a lovely comment on Facebook a little while ago from somebody when somebody was talking about Olympus Mons, and when somebody said it was 3 times the height of Everest, this person said, "How are they going to breathe at that altitude?" So
yeah, right.
Yeah, absolutely. So
because the reason it's also so high is that because of the weight of it, it's actually sinking down as well. It's
Yes,
actually
it is.
pushing
It
down
is
because
sinking
it's
into
so
the
high, and
crust.
that's why you get such massive cliffs.
Yeah.
It's actually sinking. So
Yeah.
they didn't do the foundations very good.
Yeah.
So when you compare them to mountains on Earth, you really need to compare them to mountains from, say, for example, the seafloor. If you were comparing
Yeah.
them to
Indeed.
Mauna
Indeed.
Kea,
Yeah,
not
there's
just
some
Yes,
very
because
big ones
the
there.
tallest mountain on the earth is not Mount Everest, of course, if you take it from the sea.
No, that's right.
So there we are.
Yeah.
So just Gerald, thank you so much for your donation. So it's very kind of you, as always. We do appreciate it. Thanks so much. Ian says, "What with this, Vera Rubin, SKA, and others, we are really blessed." Absolutely, Ian. Couldn't have said it better myself. It's really going to be a golden era of astronomy. What I might do for next week is have another dig around, because there are some other observatories coming online over the next few years, and I'll probably carry on with this series of telling you all about the new telescopes and observatories, because it's going to be amazing. And what a time to be alive, eh? What a time to be alive.
I mean, 'cause as I said, we did it on Astro Radio, and of course, we were looking into the future.
Yes, indeed.
Now the future is here.
Yeah,
So,
yes, absolutely.
we've time traveled
Yes,
Yeah.
slowly.
very slowly, 1 second at a time. So there we are. All right. So what we're going to do now is go over to Lou. If you're ready, Lou.
Yep, all set. All set.
And Lou's going to take us through another one of his Battle of the Cosmobots.
Oh, we got 3.
Cosmobots, bots. So today we are going to look at 3 satellites. The COBE, Cosmic Background Explorer, the WMAP, let me prepare for this one, Wilkinson Microwave Anisotropy Probe, and I'll explain all that, and then the Planck satellite. And normally when we do Battle of the Bots, we would just kind of jump into them, right? And here's this spacecraft, here's this satellite. They're studying Mars, there's Mars, they're looking for new stars, there are the new stars or exoplanets. We all know what that is, but today we're going to have to do a little physics first, because these spacecraft are looking at the cosmic microwave background radiation, the radiation given off early in the universe that contains all kinds of great information about what the universe is made of, the dynamics of the universe, dark energy, dark matter, the age of the universe. All this stuff is embedded in this light. So let's take a break for physics here now, and we're not going to do anything too advanced, but it's important to understand why we spent money launching these things and what they're going to do for us. Okay. This is a graphic that's used many times in talks on cosmology. This graphic from left to right represents the formation and evolution of the universe from the very beginning of the Big Bang up through today. Okay, so the universe is thought to have begun from a state of extremely high density, high temperature plasma, often referred to as a singularity. The universe has been expanding since the Big Bang, right? The rate of expansion is a key area of study in modern cosmology, and we often refer to that as through the Hubble constant, which we won't be talking about today, but is an important element in understanding the evolution of the universe. So, 13.8 billion years ago, the universe existed as a super hot plasma, so hot that even fundamental particles could not form, right? And then we believe it expanded actually quite exponentially at first. It's a process called cosmic expansion. And as it expanded, it cooled down. Eventually, as it cooled, as things that expand cool, right? It allowed for the formation of fundamental particles. And during all this time, from the formation of photons and electrons, fundamental particles. The photons were essentially trapped in the universe. The universe was opaque because the mean free path that a photon would travel before it hit a free electron and got scattered again was relatively small. Now, when we say relatively small, in this context, we mean perhaps 4,000 light years, right? But that is relatively small compared to the size of the universe, even at that time. So the universe continued to expand. And at around 380,000 years after the Big Bang, the universe had cooled sufficiently for atoms to form, capture those free electrons, and have hydrogen atoms form. Once that happened, the universe became essentially transparent, no longer opaque and tied to Compton scattering. And at that moment, the light from the universe was able to escape and travel, and that is the light that we're looking at today when we see the cosmic microwave background radiation. It has cooled, it has stretched, it has gone to higher wavelengths during all that time, and this is the remnant radiation given off by the Big Bang. So some refer to it as the faint afterglow of the Big Bang. And this light, which, by the way, was predicted before it was observed, so that's very powerful, holds much information about the age of our universe, its composition and relative composition of elements, the dynamics of the universe, as well as the nature of dark matter, which doesn't exist, and dark energy. So we still need to have that dark matter-mond debate there, Andy.
So just before you move off that slide,
yeah,
you just put it back up.
There you go. Wait. There we go.
Yeah. Look at the bottom. It says the first stars appear after approximately 400 million years. Well, thanks to the James Webb Telescope, we now know that figure has to be put back because we're seeing galaxies with a lot of stars, maybe 200, 250 million years after the Big Bang.
Thank you, Andy. Andy, absolutely right. Thank you for that. Yeah, and whatever follow on to the James Webb we have will probably define that even more accurately.
Exactly.
Good point. Okay, so let's march ahead here. Well, so let's see. So this strange thing is actually a telescope. But let's go back. In 1948, Ralph Alpher and Robert Herman were studying Big Bang nuclear synthesis along with the famous George Gamow. And they predicted the cosmic microwave background radiation and estimated it at a temperature of about 5 degrees Kelvin. Their results were published, but not much attention was paid to their results for about 2 decades. Then in 1964, Arno Penzias and Robert Wilson, Penzias and Wilson, while using a horn antenna that you see here at Bell Labs to investigate radio emission from the Milky Way, discovered a faint uniform microwave radiation, a kind of noise emanating from all directions of the sky. They didn't understand what this was. It was noise kind of screwing up their data. This was later identified as the cosmic microwave background radiation. And there are great stories about all the steps that they went to try to figure out where this noise was coming from, including cleaning pigeon poop off of their antenna to make sure that wasn't causing problems. But for their efforts and for this discovery in 1978, they won the Nobel Prize in Physics. The signal that they detected, that I'm going to show you in a moment, was consistent with the predictions of the Big Bang Theory, which proposed that the early universe was hot and dense, as we'd said, and that its leftover radiation would be detectable as a faint, much lower energy afterglow today. This was a major breakthrough in cosmology, provided very strong observational evidence for the Big Bang theory, and it helped solidify its place as the leading model for the origin and evolution of the universe. So let's take a look at what they discovered. All right. This, let's see, this plot is a plot of a black body spectrum. Some people call it a Planck curve, but everything in the universe, you, me, your desk, the planet Earth, everything, gives off radiation at a certain temperature. And that radiation is over a range of wavelengths. And this particular curve that you see here in purple is the black body radiation given off by an object at a temperature of 2.728 degrees Kelvin, which is in fact the average temperature of the Big Bang radiation of the cosmic microwave background. What you see on this graph here on the left, you can see the where the observations that Penzias and Wilson took, where they here they got a temperature of about 3.5 degrees Kelvin. You can see some other data points along this curve. FIRUS and DMR are from the COBE satellite, 2 instruments on the COBE satellite, and other data as well. But what is so interesting about this is that the data from these observations follow the black body curve extremely closely. And as we'll see, even closer than that. This was actually a prediction made by the researchers that were predicting the existence of the cosmic microwave background using inflation theory and Big Bang cosmology, that this energy that we saw all around us, this CMB, would be very isotropic. In other words, very much same temperature in all directions. So we'd like to find out more about this, this light, and we launched the COBE Cosmic Microwave Background Explorer spacecraft. Oops, I think that's must be one before that, I think. There we go. There we go. COBE, also referred to as Explorer 66, was a NASA satellite dedicated to cosmology, to the observation of the CMB, and it operated from 1989 to 1993. Its goals were to investigate the cosmic microwave background radiation and to provide measurements that would help shape the understanding of the formation and evolution of the universe. Its measurements provided 2 key pieces of evidence that supported the Big Bang theory. The first is that the CMB has a near perfect black body spectrum. In other words, it's very isotropic. Temperature doesn't change much. 2 of COBE's principal investigators, George Smoot and John Mather, who I actually worked with at Goddard Space Flight Center, received the Nobel Prize in Physics in 2006 for their work on the project. I think John was the project scientist. And according to the Nobel Prize Committee, in quote, the COBE project can also be regarded as the starting point for modern cosmology as a precision science.
If I could just interrupt for a minute.
Yes, sir.
If you haven't read George Smoot's book, Wrinkles in Time, which is his own account of the whole of the COBE project from when he was doing balloon experiments, which he did many balloon experiments before COBE was launched to try and detect the CMB. It's a really interesting read, and not dry and uninteresting as you might expect. There are some great stories in there, especially with the balloon experiments. At one point, one of their balloons came down in the rainforests of Brazil, and the equipment package on it contained really useful data that they had to get. But some of the natives in the rainforest held the instrument package to ransom and demanded money to return it, which actually they paid, and they managed to get the instrument package back with its useful data. It's a really good read, Wrinkles in Time by George Smoot.
Balloon missions are like that. I have other stories of balloon payloads coming down in a farmer's field and him guarding over it with a shotgun and kinds of things like that. So you don't know where you're going to land, I guess.
No, exactly.
All right. So what is all this data? Well, these are 3 images of data extracted from the COBE observations. The top one has just essentially red and blue, rather smoothed colors. The radiation here is measured in parts per thousand. The radiation is warmer to the upper right because the solar system is moving, and it's moving at a fairly high velocity of about 600 kilometers per second. And this actually has a name. It's called the dipole asymmetry. When you pull the dipole asymmetry out of the observations, you can see the picture clears up a bit. Light blue and red now represent an increase in radiation temperature of only a few parts in 100,000. And what you see in the middle of this, and this again is the middle graphic, is the temperature from the Milky Way, the glow of the dust in the Milky Way. So when you subtract that on the bottom, the radiation from Milky Way is gone. The residual fluctuations represent the temperature fluctuations of the CMB when the universe, again, was around 300,000 years old. And what I want you to notice in the bottom image is the size of the features in this red and blue image. The angular resolution of COBE was about 7 degrees, and that was the diffraction limit of the instrument. So it was the first data that was taken, but in some respects, it was fairly low resolution. So can we do better? Yes, we can. In 2001, the WMAP spacecraft was launched. WMAP stands for, again, Wilkinson Microwave Anisotropy Probe. So microwave is the wavelength range we're looking in, and isotropy means not the same temperature. Okay, so it's looking for temperature deviations in the cosmic microwave background. This spacecraft operated until 2010. It was launched to the Lagrange 2 point, which is a place about 1 million miles from Earth, going in the opposite direction of the sun, where the gravity from the sun and the Earth just balance. And by putting a spacecraft there, it can be kept in place with a minimum expenditure of fuel. And also, it can use the Earth to shield it, as it were, because remember, we're measuring temperature at very, very fine accuracies. An overview of the discoveries and implications of the WMAP observations was summarized in their mission report. And here are a few of the findings. The universe at that time was 13.7 billion years old, with a margin of error of about 1%. First stars ignited 200 million years after the Big Bang. Light in this picture, in other words, the cosmic microwave background, came from a time about 380,000 years after the Big Bang, and that the content of the universe is 4% atoms, and what we call baryonic matter, the stuff that makes up you and me and planets and everything else. 23% cold dark matter, we don't know what it is, and it may or may not exist. And 73% dark energy. So the matter energy equivalence of the universe has only 4% of the universe that we really know anything about. It was also able to deduce that fast-moving neutrinos do not play any major role in the evolution of structure in the universe, and they would have prevented the early clumping of gas in the universe, and that would have delayed the emergence of the first stars and the first galaxies, which is in conflict with the WMAP data. Well, I said we weren't going to mention this, but I will. WMAP also recovered from these observations an H naught, a Hubble constant of 71 kilometers per second per megaparsec, with an error of about 5%. Okay, so you remember the picture that I showed you from, and we're going to do some side-by-side comparisons from the COBE data. This is a picture of the universe, a picture of the cosmic microwave background radiation from in one certain projection of essentially all the universe. And what you should notice here is that the spatial resolution as well as the temperature resolution are much finer here because they had better instruments. And so we will continue on this trail to even better and better instruments. Okay. So in 2009, to go one step better, Planck was launched by the European Space Agency. It studied the cosmic microwave background radiation, and it provided even more accurate and detailed maps of the CMB, which offered even better insights into the early universe and its evolution. Planck, by the way, operated until 2013. Okay, so let's, here we go. The Planck spacecraft carried two instruments, a high-frequency instrument and a low-frequency instrument. These detectors converted microwave and radio light that was gathered by the telescope into these accurate maps of the microwave sky. We've seen two such maps so far. And this data was used to extract yet again the most accurate estimates of spatial variations and of temperature variations in the CMB. And from that, we were able to deduce formation, age, composition, and dynamics in the universe. So let's see what else to say about this. These detectors on Planck could measure temperature variations in the sky of millionths of a degree Kelvin, or if you will, centigrade. And I found an interesting way to think about this. This is similar to measuring from Earth the heat produced by a rabbit sitting on the moon. Now, where people come up with this stuff, I don't know, but there you go. And in order to achieve this kind of accuracy, you might imagine that the instruments, the detectors in the Planck spacecraft had to be cooled to about 1/10 of a degree above absolute zero. So temperature of minus 273.15 degrees centigrade, so that the temperature and the heat from the spacecraft didn't swamp the observations of the CMB. Okay, so now let's do a little side-by-side comparison here. There are a lot of things in this table to look at, but I want to draw your attention to two rows. One is the sensitivity. For COBE, it had a sensitivity of about 70 microkelvins. WMAP, I apologize for the way that's stated, it actually has a sensitivity of about 20 microkelvins, and Planck 5 microkelvins. So better, better, better. Angular resolution for COBE, as we said, was 7 degrees in the sky. WMAP, about 1/2 degree. I've seen both 1/2 and 0.3. And Planck, about 1/10 of a degree. So we're getting finer and finer measurements of the temperature variations and the size of the temperature variations in the cosmic microwave background. Okay, so here's a much better side-by-side comparison of the of the three spacecraft. You can see on the left the COBE data, WMAP data, and on the right Planck. And so finer and finer measurements, not only in terms of spatial resolution, but in terms of temperature sensitivity. Okay. Now, what the heck is this? Okay. If you plot the data from these spacecraft, those images that we just saw of temperature variations, you can plot the size of each of the temperature variations versus the temperature, or the change in temperature, if you will, if we're looking at deviations from the 2.78 degree blackbody curve. And when you do that, information about the formation of the universe pops out, but you have to know how to read it. Okay, so what you see here are three peaks identified. The first peak is an indication of how flat or curved the universe is as a whole. Since the cosmic microwave background comes from the farthest edge of the visible universe, its light can be distorted by the curvature of space, or what's called the cosmic curvature. If the universe is flat, like a sheet of paper, but in 3D, of course, then the fluctuations we observe would appear undistorted. If the universe is positively curved, like the surface of the Earth as an example, if we move down to 3 dimensions, then the fluctuations would appear magnified by the cosmic curvature. And if the universe is negatively curved, then the fluctuations would appear smaller. On the power spectrum curve that we see here, this means the first peak would be more to the left if the universe is positively curved, or more to the right if it's negatively curved. And what we find is that the first peak is about, it's about at a value of L equals 200, which is the flat universe. All right. So let's say no more about that. The universe is flat. The second peak indicates the amount of matter in the universe, which we call baryonic matter, atoms, electrons, protons, neutrons. Given the initial fluctuations in the universe, all matter would tend to be gravitationally clumped toward the higher temperatures, higher densities, right? Which would tend to reinforce them on smaller scales. But regular matter, the baryonic matter, the kind that interacts with light, the kind that we know about, the 4% of the universe, would also tend to heat up as it clumps. And the resulting pressure would tend to push against the clumping of matter. So the more regular matter you have, the more baryonic matter you have, the more pushback you would get. This means that the more regular matter there is in the universe, the more the second peak will be damped out. So the smaller the second peak, the more baryonic matter in the universe. Given the observations that you see here, we can deduce that the regular matter makes up something like 4.5, 4.9, something like that % of the mass energy equivalence of the universe. This all comes from the observations of the cosmic microwave background. Finally, the third peak, dark matter. The third peak is an indicator of the amount of dark matter in the universe. Dark matter gravitationally clumps like regular matter, but since it doesn't interact strongly with light, if there is dark matter, it isn't affected by the pressure of light against it. So the regular matter clumping, the regular matter clumping experiences a pushback. The dark matter clumping does not. So the height of the third peak gives us a measure of how much dark matter there is compared to the total amount of light in the early universe, what's known as the matter radiation ratio. And since we know the light and regular matter are related, the matter radiation ratio tells us the amount of dark matter in the universe. from this.
Can I just ask a question here?
No, you may. Oh, okay. Please. Of course. Ask them.
Why is the second peak labeled baryonic dark matter? Isn't that a contradiction in terms?
I think what we're seeing, it's the total amount of matter, baryonic and dark.
Oh, right, baryonic and dark matter.
Yeah.
I understand, right.
And
Thanks.
so then from the third peak, if you can derive the amount of dark matter, then from that you can backtrack and get the amount of baryonic matter.
Thank you.
Yep. So where was I? Yes. So for the third peak, we are able to derive that dark matter makes up about 26.8% of the mass energy of the universe. I find this to be almost witchcraft. It is remarkable. And what is even more exciting about this in a way is all of the math you have to do to get to this. So we went over almost essentially no math here, but the people who come up with this, who are able to say, these are the temperature variations, these are the sizes, and therefore the universe is this way, I think are absolute magicians.
It's amazing, isn't it? Absolutely amazing.
It's amazing. So I will stop there, and if there are questions, please put them in the chat, or our panel can just ask away.
Thank you very much, Lou. And it's amazing that we can deduce these things just by looking at those colored blobs in the microwave background, isn't it? It's just, what stories it actually tells is just absolutely amazing.
It is, and so what we want to do is we want to pull this information out of the CMB, and then we want to look at the universe we have today. And if the information that we're pulling out of the CMB is reflective of the universe that we have today, we can say that the results are consistent with the lambda cold dark matter model.
Yeah.
Okay, with the cosmological model of the universe.
Absolutely.
Doesn't mean it's the way it is. It just means it's consistent.
There we are. Thank you so much for that, Lou. Really, really interesting.
Yeah, because when you were talking about the discovery, the original discovery of Mr. Penzias and Wilson.
Penzias and Wilson.
Yeah, they, as you said, they had a lot of trouble, and they were really at their wits' end because they had this constant hiss in all directions, and they couldn't work out what it was. And they actually approached Robert Dick and Jim Peebles and Dave Wilson and sent them a paper they'd written. And it turns out that, as you said, Dick, Peebles, and Wilson were also looking for the dark matter, the cosmic microwave background. Sorry. And as soon as they read the paper and they heard about the hiss, Robert Dick turned around and said, "We've been gazumped." Basically, they found it, and in the end, they actually combined themselves and they wrote a joint paper. But yeah, one of the things I can always remember, if you can remember when we had the old tubes for the televisions, and then when it was detuned or at the end of the night, you had that hiss and all that stuff glowing and glittering. All that was part of that. A portion of that was the hiss of the CMB.
Yeah, so, that 1% of it, wasn't it?
Yeah, so it was there all the time, and we were watching it.
Yeah.
For the sad sacks who were up late.
It's a shame we can't do that anymore to show people the Big Bang.
Exactly. Yeah. Science in action. You say part of that is the constant microwave cosmic microwave background.
Yeah, amazing.
It's interesting, isn't it, how many discoveries are made by accident?
Right?
Yeah, if you go through the history,
it was that way, right?
Yeah, absolutely. Okay.
If you go through the history, it is sort of like serendipitous, a lot of it.
Yeah, definitely. Okay, well, thank you very much, Lou, for that. Very, very interesting. And viewers, as always, if you have any questions or comments, put them in the chat. Thank you, Sandra, for your donation. Much appreciated. Every bit helps to keep us going. That's very kind of you. We do appreciate it, as we appreciate all your donations. But of course, what we love most about you lot is just you being here every Tuesday. And we're so glad that you are, and sharing these wonderful stories of the universe with us. Okay, we're going to move on now. It's time to don the hazmat suits and open that door and reveal the horrors that lay beyond in the form of Einstein of the Week, where we take a look at some of the amazing things people say about the universe on social media. This week, it's a bit of a special edition. It's a themed Einstein of the Week. Let me explain why that is. This is all about the DART mission. Now, cast your mind back to 2022. NASA attempted to change the orbital path of an asteroid called Dimorphos as it orbited another asteroid called Didymos by slamming a spacecraft into it, essentially. Why did they do this? They did it ultimately to save lives on this planet, because as we know, sooner or later, the Earth is going to be threatened by an asteroid impact. And we need to develop technologies to deal with that. This was the first experiment to try a new technology to see whether it's possible, in the event that an asteroid were threatening the Earth, to knock it off course. And obviously a small scale experiment, but it was the first. And they successfully changed the orbital period of Dimorphos around Didymos by nearly half an hour by slamming a spacecraft into it. Now, what's been in the news the last couple of weeks is that the resulting cloud of debris from the impact of the spacecraft with Dimorphos did not go the way that astronomers thought that it would. Instead of the debris being ejected in all directions equally, it clumped, and it was given off in two specific directions. The reasons for this are unclear, but the European Space Agency has a spacecraft on the way to study the impact to try and work out what exactly happened, because it wasn't exactly what we were expecting. Now, obviously, if you've got something like Dimorphos, which is basically a pile of rubble made up of stones, if you like, stones and boulders, trying to predict where all of those individual stones and boulders will go when you slam something into it is virtually impossible. Not even the world's biggest supercomputer could give you an accurate prediction as to where each stone and boulder would end up going. But this is very interesting, that the debris was scattered off not equally, but in more or less two directions. And we don't know why. So hopefully the European Space Agency will be able to shed some light on it. Why am I mentioning all this? Well, this story came up on Facebook, and there were a lot of comments about this. And quite a few of them were worthy of Einstein of the Week. So this is the DART Einstein of the Week special. So the first thing was we had a rather cheery soul commenting on the news about the DART mission. And this person said, "Mankind, judgment day is upon you. All world religious and cultural leaders are about to perish along with billions of you. You tore asunder and joined together everything you shouldn't have. Those that survive the cleanse will clean this planet before you are terminated and judged like never before." So
that's a bad day.
Yeah, somebody's having a pretty bad day, really.
Well, that's rained on my parade.
Yeah.
Yeah.
Let's pool our coffee money and make this guy a bet.
Yeah.
Okay?
Yeah, because tore asunder and joined together everything you shouldn't have.
Yeah.
Yeah. He said that is all doomsday stuff, isn't it?
And apparently judged by an alien. There's an alien in
Yeah,
this.
by the look of
Yeah.
it.
Is
Yeah.
that? Or I don't know.
An alien with 3 eyes
Yeah.
and a superhero logo on his chest.
There's only one eye in alien.
Is that an alien?
Yeah. So there you go. So there's a cheery soul for you. The next one of our DART mission Einsteins is no control. Humans have zero control over celestial bodies. Better leave that to the maker. So there we are. Apparently we're messing around things that we shouldn't be. We do have control over celestial bodies, believe it or not.
The data the data would say otherwise. We pushed Dimorphos enough that we were able to measure it.
Exactly. So
Yeah,
there.
so, I mean, obviously that's a religious reference, but he's got a bit of a pretentious second name.
Yeah.
Hmm.
Life of
Saint,
Brian.
Yeah.
Saint Brian.
Yeah. So there you are. So the next dark mission Einstein, crazy weather. You might already guess where this is going.
Oh, yes.
Maybe this type of scientist behavior is what's causing all the crazy weather catastrophe on our planet.
Oh dear.
How would you test that? That's
We're all doomed.
We're all doomed. Yeah.
Yeah.
So I did actually reply to this person. Well, actually, no, to be honest, I replied to a lot of comments in this post, just restating what the aims of the DART mission were, what it was all about, because obviously they hadn't understood the first thing about it. But I replied to this lady, and she replied and told me she'd had enough of my demonology. So,
well, I wasn't going to say anything, Andy. But...
No.
I like this one, Andy.
It's great, isn't it? So all of that crazy weather is due to NASA impacting an asteroid a long way from the Earth. Can't anybody remember how far away Dimorphos is from the Earth? I can't remember.
I don't know.
Long way.
Yeah. The deep burrito's got it.
Yeah. Yeah.
You know,
I can't see the comment at the moment. What does the deep burrito say?
It's at the bottom.
Destroyed an alien art piece, and they want payback. Oh no, Hollywood will actually make this movie.
That's it.
They already have that point. Aren't there 2 or 3 movies about destroying or moving or something?
Yeah, Deep Impact. And Bruce Willis.
Bruce Willis will be in it. Yeah.
Yeah.
And probably Morgan Freeman as
Oh,
well.
Bruce again.
Yeah, Bruce again. Yeah. Okay, moving on. Dark Mission Einstein is altering the universe.
Oh, okay.
Here the Earth was just through the universe and obviously that's minding its own business when the so-called scientist, singular, decided to strike it with a missile, thereby creating a chain of reaction that could literally alter the universe and end our planet as we know it. Good job, NASA.
Yeah, right.
So we've gone from altering the weather now to completely altering the universe.
Yeah.
Ooh. Wow.
Yeah. It was a big job, so we probably but it's the chain reaction bit I like.
Yeah. Absolutely.
Yeah, Diana Ross, that is.
Yeah. Say your prayers tonight, guys.
Yeah.
Yeah.
There we are.
Yeah, good job, NASA. I agree. Yeah, good job, NASA. You hit it.
I agree. Yeah. And then lastly, playing God. Again, playing God. Will we ever learn? The answer is no, not until we destroy Earth. Now, the irony of this, of course, is that the DART mission was the first attempt to develop technology so that the Earth doesn't get destroyed. Obviously the irony is lost on this person. But it was a really, really depressing experience reading through these comments. If this is the intellectual level of people when we're talking about saving the Earth from disaster, then it reminded me of the film Don't Look Up, to be quite honest. So it's depressing that there are so many people who just don't understand or choose not to understand and who have it in for NASA apart from anything else. So it's you see what I do for you viewers. I depress myself going through these social media comments every week to bring you Einstein of the Week. So you know it is immensely depressing that in 2025 people hold such ridiculous views and opinions and ideas.
There's something interesting about the psychology of all this.
What's that?
I think it was it 2012 that the Mayan prophecies, the end of the Earth. Okay, so I did a little research and wrote an article on doomsday prophecies, and it seems to me after all this that many people love to predict the end of the Earth. They love it so much that ministers, I think these were kind of TV evangelists would say, God spoke to me and the earth is going to end on April 9th. And then it didn't. And then he said, well, God changed his mind, came and said, no, it's not going to be April 9th. It'll be, July 3rd. And then it didn't. And then people still hung out with this guy and believed what he was saying. Some people killed their children so that they wouldn't have to suffer the pending end of the earth.
Really
Strange thinking and unfortunate thinking.
It's like the Branch Davidians, wasn't it? And David Koresh, and when people committed suicide because they thought that Comet Hale-Bopp had an alien spacecraft hiding behind it. It was intensely depressing.
You know what I heard about that? I haven't verified this, but this would be something to check into, that that star maps did not show anything behind the star that was where the spacecraft was supposed to be online, star maps. And it was because the threshold for the apparent brightness of the stars was set too low. Otherwise, they would have seen that the thing trailing this star was, in fact, just another star. And perhaps all of this would have been avoided. But have you all heard anything like that?
No, haven't heard that.
Not about that star one, but with the, like Andy was saying, with the cults and all that. I mean, some of them, they believe that their alien masters were coming to collect them, but they couldn't be taken in a physical form, so they had to, basically commit suicide, unlive themselves, if we got to say.
That's right.
And the whole cult basically committed suicide, and so that their so-called spirit or being, ethereal being, could be taken by the aliens. I mean, so these things are quite strange, because, like I say, the 2012 Mayan calendar fiasco wasn't actually a prophecy of the end of the earth. It was just that they came to the end of the calendar and it recycled. It's like we come to December, then we go back to January. And that's what the Mayan calendar was doing. But everybody, I mean, it produced some good films. Films anyway. Films. Yeah, but people like to read things in it that don't actually exist. So yeah, it's very strange. I mean, looking at all those that Andy just put up, there was one glaring theme behind them, and most of it was sort of like other than that. But there was a thread running through it if you read them again. It's just very strange that people tend to take these views and basically they'll prophesize them. Because I mean, I was telling Andy the other day when we were talking about Einstein of the week, that I saw one. I think it was one of our members, Susan Snow, put one up, and it was somebody rabbiting on about us seeing further and further, using the James Webb and other big telescopes, optical ones as well. And it was saying because we are actually zooming in onto further and further away stars, galaxies, and things like that, we were actually physically stretching obviously in the telescope, physically stretching space and time. And they said if we keep going on, we will actually tear the fabric of space, and then we'll all disappear. So okay, then that was I thought, yeah.
But do you want to know what I find most depressing is that whatever the subject of a post on social media, in this case it was DART, but it doesn't matter whether it's James Webb or Vera Rubin or anything else related to the universe, there is so much naked hostility towards science. And NASA is the whipping boy, because a lot of Americans don't realize that NASA is just one of 78 space agencies around the world. And all
There are others?
Yeah, there are. Yeah. Yeah, better ones like the ESA, for example. So, so it's naked hostility towards science, and it's extremely worrying that there is so much hostility towards science when paradoxically everybody has more science available for them to look at and understand than ever before. But where this hostility towards science comes from, I don't know. I mean, a psychologist could probably write several books about it. But this anti-science sentiment among the public is on the rise rapidly. It's got to the point where on social media you cannot have a scientific discussion, particularly on Facebook, without seeing this incredible hostility towards science, towards learning, towards knowledge. It's worrying, and it is accelerating greatly. That's what I want. So let's
it's almost as if we've gone back centuries and centuries when the Earth was the center of the solar system and the sun revolved around the Earth.
Yeah, indeed.
It does, doesn't it?
Yeah, indeed.
Well,
I mean, unfortunately, this goes back to, especially with the younger generation at the moment. They're the worst. Is they're not taught critical thinking anymore?
They were never taught critical thinking.
They basically they believe everything that they're told.
Well, now I don't know about that.
I do.
I have three kids who would beg to differ. I bet the rest of us could come up with examples.
Exactly. I mean, maybe I was being a bit harsh there, but most of these colleges and all that and universities, they don't teach them because they're all learning these. I mean, yes, there are people doing the sciences and STEM and all that, but there are a lot of them just doing these sort of like social courses, and these are the ones that basically they just haven't got a clue how to think for themselves. It's really, really strange. But yeah, I've had conversations with lots of youngsters, and I think I've got to walk away because they just haven't got they can't think outside the box. They've got no ability. And once you start criticizing them, then of course then you go down another road, which we won't go into.
Yeah.
But
Anyway, Alan says, is it actually worth saving the Earth with so many zero IQ types out there? And that's a very, very good question. Paul says, at our age, hang on, it's coming up. We have all lived through quite a few ends of the Earth.
Yeah.
Very true.
That's
very
true.
Sandra says Hollywood has a lot to do with it. And it's very true because, Hollywood generally portrays science in a much simplified light and not really what science is all about on the whole. I mean, there have been some great movies that portray real science, like Contact, for example, which was a great movie. But on the whole, science is dealt with not very well, and scientists in Hollywood movies are always geeky types who you'd never invite to a party. So yes, you're quite right, Sandra. Sort of Hollywood has got a lot to do with the portrayal of science.
But when the 50-foot spider climbs over the mountain towards your town, who do you run to? You don't run to your accountant. You run to the astronomer in the observatory. What do we do?
But this was this was what I meant about the DART thing, that there was so much hostility towards scientists who are only trying to save lives on this planet and avert disaster. And that I cannot understand at all. They will be the first ones complaining when the Earth gets smacked by an asteroid. They're living in a cave. They'll be saying, why didn't the scientists do something? Well, scientists are doing something, and the DART mission was the first step into doing this. But that hostility I towards people who are trying to save their lives, it's just beyond me. Anyway, let's move on. So thank you for all your comments, viewers. And we're going to move on to Michael now. Oh, yeah. Now, don't say you weren't warned. So if I could just find the relevant scene here.
I'm going to share my screen.
Oh, okay, if you must. Go on.
Right,
Michael is going to deliver Constellation of the Week to you this week, so take it away, Michael.
Okay, so here we go. How's that?
Looks good.
Lovely.
Okay, so tonight our Constellation of the Week is Lacerta the Lizard.
Aha.
A hidden gem in the northern celestial hemisphere, Lacerta is the Lizard slithers quietly between its more famous neighbours.
I see what you did there.
And there's a diagram of where Lacerta is. You got them straddling the Milky Way there. But it's quite faint, unfortunately. But let us go through it. Unlike many constellations with ancient mythological roots, Lacerta is relatively modern, introduced in 1687 by Polish astronomer Johannes Hevelius in his star atlas Firmamentum Sobieskianum.
Hey, well done.
Sobieskianum, I think. Okay, right.
What does that translate as, Michael?
Good question. Hevelius created 6 new constellations, including Lacerta, specifically to fill the gaps in the northern sky that weren't mapped by ancient astronomers. Originally named Stelio after the genus of lizard now known as Lodeucia stelligama.
You've really made a rush for your own back with this one, haven't you?
Yeah.
It was later replaced by the Latin Lacerta, meaning simply the lizard. The alpha star is still called Stelio, which I'll come to in a bit. Okay, and this is the lizard concerned. Okay.
Does it have a name?
That's what I just said.
Oh, right.
Dave, yes, called Dave.
No, yeah, I was going to say, is it called Dave or something?
Yeah, probably. So this is the constellation surrounded by other more well-known constellations: Cygnus, Cepheus, Cassiopeia, Andromeda, and Pegasus. Okay, in the night sky, the location situated in the northern celestial hemisphere near the Milky Way. Neighbours, as I say, include Cygnus, Andromeda, Cassiopeia, Cepheus, and Pegasus. Best visible from latitudes plus 90 to minus 40, especially prominent in October evenings. It covers 201 square degrees, ranking 68th largest of the 88 modern constellations. Okay, its bright stars form a distinctive W shape, although it's very faint, so I'll come onto the magnitudes shortly. But apparently it does have the nickname the Little Cassiopeia. You can just about make out a W shape there. The constellation's outline resembles a slender lizard slithering across the sky, as you can see here. Not totally circumpolar, Lacerta partly dips below the northern horizon in February as viewed from the UK latitudes. And this is an ancient diagram of Lacerta I found. Unlike many constellations, as I've said, Lacerta has no classical myths associated with it, reflecting its relatively recent creation in astronomical history. In Chinese astronomy, however, northern Lacerta was part of Tengshe, the flying serpent constellation composed of 22 stars. And this is what this diagram depicts, actually. This cultural connection was recognized in 2024 when the International Astronomical Union officially named V2424 Lacerta Tengshe to honor this heritage.
Good for them.
Lacerta's modern creation reflects the scientific spirit of the 17th century, filling a celestial gap with a reptilian motif rather than drawing on classical mythology. Okay, the key stars then. Alpha Lacertae or the Stellio, brightest star in the constellation with a magnitude of 3.76. A blue-white main sequence star approximately 102 light years from Earth. Beta Lacertae, a yellow giant star with a magnitude of 4.4, located 170 light years distant from our solar system. And 424 Lacertae or Tengshe, a variable star named after the Chinese flying serpent figure, part of the ancient Chinese celestial mapping traditions. The constellation contains 12 stars known to host exoplanets, including Taika or HAT P40 and Tengshe V484 Lacertae. Deep sky then, nothing special really. Caldwell 16 or NGC 7243 is an open star cluster about 2,500 light years away, visible in small telescopes. That's the best picture I could find of it, I'm afraid. BL Lacertae is a prototype blazar, a type of active galactic nucleus with jets, namesake of BL Lacertae objects. And that's the actual object there, pointed by the arrow, of course. And IC 54217 is a faint planetary nebula. Okay.
Gosh, that is.
Yeah. So may not get much on a sea star, I think. Okay, scientific and observational importance. Magnetic phenomenon Lacertae contains Babcock's magnetic star HD 215441, known for its extraordinarily intense magnetic field, one of the strongest measured in any non-degenerate star. Stellar flares. EV Lacertae is a remarkable flare star capable of producing a powerful stellar flares visible from Earth, making it an important target for studies of stellar activity. Didn't get much more on that, I'm afraid. Constellation's location along the Milky Way makes it a fertile hunting ground for amateur astronomers exploring star clusters, nebulae, and variable stars. Not sure about that either. A subtle jewel of the northern sky. Though faint and modern, Lacertae offers fascinating glimpses into star formation, variable stars, and active galactic nuclei. Its unique history and cultural ties enrich our understanding of how humans map the heavens across different civilizations and eras. Next, clear autumn sky, autumn night, seek out the lizard slithering quietly amongst the stars and discover its hidden wonders. Okay.
Thank you very much, Michael. Lacertae, not an impressive constellation, but it does contain this prototype blazar. So interest because of that. Just to point out about the jets, it's called a blazar because a blazar is an active galactic nucleus whose jet is pointing right at the Earth. So it's very different to
and it's not something you wear to school.
No. So there we are. So yes, thank you. That's Constellation of the Week. We'll be back with another next week. So we're going to finish off today by coming to Daz, and Daz is going to tell us about some solar storms that we've experienced, extreme solar events that we've got away with without being damaged too much, I believe. So anyway, Daz, over to you.
Right, can you hear me now?
Yes.
Yes.
Yeah, right.
How?
Okay then, so here we are. Last week I was talking about how we decide how we discern whether or not a solar storm is a Carrington type event. And as I said, there was 5 characteristics we can measure and look at to determine this. Basically, it's very hard to do because every solar storm is different. And the reason we look at Carrington events is because by our understanding, first of all, it was the first time we actually witnessed by eye a flare go off. And then with the magnetic storm that came 8 minutes later with the X-rays, and then the aurora, because at that time, remember, it was 1859. We didn't have all the assets we got now. So it was very hard to decide. So we determined last week it's almost impossible to say what was what. And if you remember, it was because of a question that was asked a couple of weeks ago in our after show party when the drinks were flowing. The question was last year in 2024, was the May or the October solar storms, which was the strongest? So that's how that came about. So, oh, hang on, I've just got to, just bear with me a second. Got to go over here, on here. Right, so here we go. So, what we have, this is a comprehensive examination of 10 most significant geomagnetic storms of disturbances to impact our Earth since the Carrington event. So we're looking back towards that. There were events that were recorded before this happened, but we're not going to really go into those. And it looks like I've cut off the bottom of the actual description there. I do apologize. Oh, it's all the excitement. So here we go. So understanding geomagnetic storms, just a quick revision. Geomagnetic storms occur when solar winds, shock waves, or cloud of magnetic fields interact with Earth's magnetosphere, causing rapid changes in the configuration of Earth's magnetic field. These disturbances are measured using indices such as the DST, which is disturbance storm time, and KP index, with the most severe storms reaching G5 on the NOAA space weather scale. And that's what we were talking about last time. So Carrington event, of course, that was the 1st or 2nd of September. Now, what we're going to do is the parameters will give us what we, especially with the older ones, when we didn't have the instruments to measure them, we reversed engineered them so to give us some idea of how strong and how violent they were. So we've got solar wind speed was estimated at 2,000 kilometers per second. I mean, that's shifting a bit. Particle density known, not known, but it been engineered to re-engineered to be extremely high on the information that we have got. Magnetic disturbance that hits, of course, we could measure that because we had magnetometers. Was 1,760 nanotesla, which is high. And the transit time from actually visually seeing the flare to the main storm was only 17.6 hours, which is a record, which at the time was a record fast. Aurora visibility reached the equatorial regions, down as far as 23 degrees north. And of course, when we talk about aurora in these times, it was visual. It's what they could see with their eyes, not with the cameras. So if we had cameras, it would have probably gone all the way to the equator. SID, extreme radio frequency emissions. Telegraph systems were a while were failed. This is if we get hit again. And telegraph papers caught fire. Well, of course, we knew that because it was in the newspapers. The telegraph hadn't long since been invented. It was beginning to be used. There was lots of cables being stretched across the USA and Europe, and we had some fun and games with them basically because of this thing. And this is why we use this as the benchmark for all storms. So, and then telegraph operators receive shocks, as we know. And it was named after Richard Carrington, which we spoke about last week, if you want to have a look back at that. So, and he was the first person to actually see, well, it was him and a bloke called Hodgkinson, who was viewing it at the same time somewhere else, who actually watched the flare go off. But it was Carrington who drew the actual sunspot that it came from. So in May 19, now these aren't in chronological order, but in May 1921, New York Railroad storm. The railway storm earned its name from dramatic effects on railway infrastructure. Represents one of the most powerful geometric storms of the 20th century. So the parameters: the solar winds was 1,700 kilometers per second. Particle density was between 50 and 60 protons per centimeters cubed. And that's what we do, just basically measure how many high energy particles pass through a very small detector. A magnetic disturbance was 900 nanoteslas was recorded. That's the magnetic storm aura. Aurora visibility 40 degrees latitude. Of course, remember that's north and south. Telegraph systems disrupted. Well, of course, we moved on a little bit from before. And what happened in New York Central Station was that the induced currents in the cables, because also you had the telegraph running through there. It actually managed to set fire to a building, which disrupted a signals tower and the telegraph system all over the USA. And the same was repeated in Europe. So that was the railroad, and I encourage you, if you're interested in this, to go and have a look at them. They're online, and you can pick up most of this. So the geometric storm of 13th to 14th of March 1989. This one was 1,400 kilometers per second, so that was traveling some. The peak particle density was 40 particles per centimeter cubed. The magnetic storm was at 589 nanotesla, and the KP that it actually reached was 9. Well, of course, we only go up to 9, but that would have been a KP 9 plus, and it was sustained for 9 hours. That storm went on, and as you can see, you can probably see already, all these are different values. So that some are scoring high in one part, but not in another. But the Carrington event, when they re-engineered it, and they think that they've seriously underestimated it, but that gets either gold, silver, or bronze in all categories, where some of these will only pick up a gold or a silver or something like that. So the Great Geometric Storm of March 1989. And of course, it was caused by a large flare, an X15 flare, followed by a massive CME, which was traveling at 1,900 kilometers per second. So this is a really fast one. And particle densities of approximately 25 protons. So we've dropped down. Magnetic disturbance, extreme severe, with DST reaching 589 nanoteslas, and again the KP index of 9, which is G5 on the modern scale. And that, as I said, that was for 9 hours. The entire province of Quebec suffered a 12-hour blackout after the storm collapsed, and Hydro-Quebec power grid it actually crashed in 90 seconds. The March 1989 storm induced ground currents that saturated transformers of the Hydro-Quebec system, with a rapid collapse of the whole system. Over 200 power grid problems reported across North America. So, of course, we're not just talking about Quebec, but this is what this one is known for. GOES weather satellite communications were disrupted, so we lost for a while on one of our satellites. Spacecraft anomalies reported on numerous satellites, and some of them went out of control. An aurora visible as far south as Texas and Florida. Sorry, did somebody say something?
No, it was
Sorry, guys, just a quick one. That storm must have been when I saw the aurora in Yorkshire.
It possibly was. Yeah, it possibly was, because as it said, these storms aren't just locally to one area; they're worldwide. And of course, when we're talking about the magnetic, when we're talking about radio blackouts, that happens mostly, well, virtually all of it happens on the daytime side. It doesn't happen on the nighttime side. In fact, during the nighttime, if you've got a solar storm hitting on the daytime side, usually enhances radio. propagation, so you can actually
All
fall
right.
further and things like that. So yeah, so it possibly was right. The Halloween storms. Now, most of these storms, as I was talking about, they're usually a conglomerate of many storms. And what will happen? I mean, I've spoke about coronal coronal holes actually inducing enhanced solar wind, which will push these storms along and make them faster. Um, Now, also, when you get a lot of these storms kick off, they will travel to Earth, and what they will do is they will actually cleanse the area between the sun and the Earth. And then if you get a big storm kick off, it's got nothing to interrupt its path all the way to the Earth. Because if it meets up with the other storms, it will get slowed down. But then that then has a knock-on effect as they all bank up, and then when they hit, it's rather than just getting one big hit, it's like a little machine gun. They go bang, 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 depending upon how many are involved. So solar wind speed on this one, 1,900 kilometers per second at its peak. Particle density, 30 protons centimeters cubed. Magnetic disturbance, 383 nanoteslas. And aurora visibility reached 30 degrees latitude. And remember, like I said, this is north and south. Um, Significant radiation hazards to astronauts. Again, so what they had to do is on the International Space Station, the astronauts had to move to um, they've got one unit up there, which is basically the walls are water tanks, and they can sit in there, and then they are saved from the enhanced radiation. Again, flights, as I said before, if you fly across the North and South Poles when these are going on, you'll receive more radiation. So flights were diverted away from the polar routes. Power outages in Sweden, HF radio blackouts for the days, for days. This is just sort of like a little bit of an infographic saying how it impacts satellites, because of course, as going back to 1859, we had no satellites, and the more and more satellites we put up, the more and more chance that there's going to be some damage done by these solar storms as they come. Even if they don't destroy or knock out these satellites, they will degrade the instrumentation on them a lot. I think there was an Intel satellite that when it was hit by a storm, its solar panels were degraded by 5%. So it lost 2 years use of those solar panels. So again, this is the Bastille event. This event started on Bastille Day, the 14th and 16th of July 2000. Wind speeds 1,800 kilometers per second. Proton density, that's 15 protons. So there's not very high radiation storm on this one. Magnetic disturbance, 301 nanoteslas. Transit time, 27 hours. So that's just over the 24 hours which we usually classify as a Carrington. Aurora visible to 40 degrees latitude. Significant radiation storm, NS4. Japanese ASCA satellite lost attitude control, and minor power grid fluctuations reported. Scientific significance: major storm with the comprehensive satellite monitoring, enabled refinement of space weather prediction models, demonstrated connection between flare intensity and CME speed, which of course we didn't know at the time. And then we move to now this one. This is where it starts to get a bit serious. We're going back in time to May 1967, and this was the Cold War crisis storm. What happened is the event hit in May 1970 and caused a crisis, and the United States military suspected that the Soviet Union was about to attack. But in declassified documents recently, because we didn't know any of this at the time, but declassified documents reveal this geometric storm nearly triggered a nuclear confrontation. So we had solar wind speeds. You can read that. There's 1,500 kilometers per second, 20 protons per centimeter cubed, and the 387 nanoteslas. But what happened is they lost communication with tracking stations in Alaska, Greenland, in the UK, because this storm, the radio in a storm that actually hit, they just basically lost communication. They thought Russia were playing games, so they actually went to the top grade. They had their finger on the button. All military units and air forces were notified, were put on standby, and the finger was literally on the button. But luckily, what happened was, sorry, I'll just go back to that one, because what happened is by this time the military and NASA and everyone else were beginning to take notice of what was happening with solar flares and how they interact with us on Earth. So they were able to suddenly, all the scientists were able to say, "Whoa, whoa, whoa, whoa! Take a step back. This is," and they were able to prove to the military that there was not a missile attack in progress. So that was, again, that was where science actually helped save the planet. It came that close, literally. It came that close. But we didn't know this until it was declassified. And here's another one that we didn't know about until it was declassified. August 1972 solar flare. The solar flare erupts with X-ray classification estimated in X20. Now that's probably underestimated. CMEs arrive at Earth in record time. This is the fastest one that's ever hit us, 14.6 hours. The magnetic storm was 125 nanoteslas with wind speeds up to 2,400 kilometers per second. And widespread aurora, radio blackouts, and navigation disruptions, as always. The more we depend upon electronics and satellites, the more we're going to have trouble with these things. But this one actually triggered, I don't know if I put a slide up, this event occurred between Apollo 16 and Apollo 17. In fact, it first hit when Apollo 16 was actually returning. So it was lucky that the astronauts were not exposed to too much in the increased radiation. But if they'd been in space at the time, they could have received potential lethal radiation doses of 1,400 rem, which could prove to have been lethal. But also, what happened is, like I said, it's hit so fast because, again, it was lots of the all week before. There've been lots of flares going off, lots of things going on, and it had cleared the space between the sun and the Earth, and it had a free run at us. And what it did is, when it actually hit us, it created a magnetic pulse, and that in turn, oh, I haven't put it on there, and that in turn actually, um, in North, we had the Vietnamese War going on, and when that actually hit, in the period of about 3 minutes, over 4,000 electronic sea mines exploded, because the pulse, because they were magnetic mines, they look for the change in magnetism as a boat goes over, and then it'll explode. But the settings that they were at, the actual magnetic pulse that was set off by this actually hitting us by squeezing our magnetosphere so fast, giving it a real good slap, actually set off all the mines. So again, this is another one we didn't know about until declassification. Superstorm, February 1956. Again, very fast winds, 1,200 kilometers per second. Particle density 25. But of course, we've had them up to as high as 40. Magnetic disturbance 414 nanoteslas. Associated with multiple X-class flares. As I said, we can get all these things go off one after the other, and they can run over days. This event featured a high cosmic ray ground level enhancement ever recorded, with neutron monitors registering 5,000% increase above normal ground levels. So that was a hell of an increase. This is just sort of a list of events and how strong they were, intensities. So St. Patrick's Day storm, I haven't got much on this one, unfortunately. Initially predicted as a minor G1 storm, it unexpectedly strengthened to G4 severe, catching forecasters off guard. Solar winds, not very fast, 700 kilometers per second. Well, I'll say that, is fast. Again, 40 particles per centimeters cubed, and with a magnetic thump of 223 nanoteslas, and it became a KP8 event. Navigation caused significant GPS errors of up to 50 meters in high latitude regions, affecting precision agriculture and aviation. Geometric storm physics. I'll let you come back and have a look at this. What we're actually looking for to actually assess these storms. This is just how the visibility of because we measure the storms in G1, G2, G3, how low the latitude you're probably going to see them at. And of course, if you've got cameras, you're going to see them a lot lower. Modern monitoring infrastructure. Well, as I said, we've got the space-based observatories. So we've got SOHO, and we've got Stereo, Discover, and the SDO, Solar Dynamics Observatory. Plus, there's also the Parker Solar Probe. There's others as well, but there's too many. But these satellites provide critical early warning of incoming solar storms with lead times of 15 to 60 minutes, depending upon solar wind velocity. Modern vulnerability, of course, we've got satellite systems, and we've got single event upsets its electronics, surface charging damage, orbital decay. Again, because when we get these storms hit, they squish our atmosphere, and it actually pushes some of the higher orbiting satellites out into interstellar space, so they're exposed. And star tracker confusion from radiation. We've also got power grids. You can have transformer saturation with transformers melting, but since we've had these storms since 1989, companies are really looking into changing all of this and making sure the system is safe. Harmonic resonance along transmission lines, protective relay malfunctions, potential for cascading failures, where we saw that, and communications, HF radio blackouts, GNSS and GPS position errors, satellites communication interference, and submarine cable repeater. When I was just talking about the squashing of the atmosphere, of course, we can remember, I think it was 2022 when there was a launch of uh, Starlink satellites, and because there was a solar storm happening and the atmosphere had been compressed, the satellites, when they were released, were in a thicker um, uh, 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 atmosphere, and they couldn't achieve orbits. And of course, as a result, they returned to Earth, as we can all remember seeing those sites. Key takeaways: historical perspective. Carrington events remains the outlier, with magnitude storm strength twice as any modern event. This suggests modern technology and structure has yet been tested by a truly extreme storm. Yeah, we're still expecting one. Despite improved forecasting and monitoring capabilities, we're still vulnerable, basically. Um, and continued investment in space weather, research, monitoring capabilities, and infrastructure and hardening is essential to mitigate future disasters. So just to go back to the original question, which was the stronger? Was it the May 2024 event or the October event? Well, basically, I'll just quickly go through this. You can see, comparing the two storms, you can see straight away that the October storm was, in virtually all aspects, a stronger storm. But until you actually look at the data, you can't really tell which it was. So basically, the October won out. And there's just some more information of where the aurora was on both of the uh, hemispheres, and some of the effects, high frequency radio blackouts for 4 to 6 hours duration, and delayer absorption. Well, we'll talk about it some other time. So essentially, again, this is just stuff that we can actually look at, comparing the two, and how they affected the Earth or our satellites, power grids, and navigation communication. And again, you can see October 1 out on all of them again. Just as an update on, because we were talking about sunspot numbers increasing. As you can see, we've had the results for last month in. The count is still going up. We're coming back up to predicted levels of sunspots, but it also means that the sun is becoming more active again. And if we have a look at this, this is we're looking at the far side of the sun, because I think it's the so the solar orbiter is actually on the far side of the sun at the moment. So what we're looking at is what's in orange is on the far side, what's in grey is what we're looking at here. And if you look on the left-hand side where it says East Limb, just below there, you'll see there's this big clump of uh, active regions just about to come back onto the sun's face. And as you can see, we've already got some quite big active regions already on the sun's face. But the ones that have gone past over the West Limb, these dark patches are the old systems that have gone off of the face of the sun, but they are deepening. So it looks like we're going to get some more action. And just to finish off, this is today's photograph, and you can see it's sort of like between the 10 and 11 o'clock region, that big cluster of new active regions is just coming onto the face of the sun. So we may be being able to see some increased action. So just keep an eye on your alarms. So I believe that's it. So that's it. So
thank you very much, Daz. Thank you very much. Very interesting. Just to go back to what we were talking about earlier, if you could just clear your slideshow.
Yeah, oh, sorry, I'm using the wrong mouse. There we go. Sorry about that.
That's okay. Just to go back to what we were talking about earlier, yet again on Facebook, there was an article posted about the sun and current solar activity. And somebody was complaining like hell that he didn't want his tax dollars spent on studying space weather, because he said if they can't get the weather prediction right on the Earth, how are they meant to get it right in space? So, so you know, yeah, they're everywhere, I'm afraid. Okay, well, listen. Next week on Space Oddities, we have a special guest next week. Lou, do you want to tell us who our guest is for next week?
Sure. Next week, we are going to have the only Dr. Sten Odenwald, a brilliant Harvard astrophysicist who has written 20 or so books now on astronomy, covering missions, covering space weather, covering astrophysics, you name it. He is really dedicated to communicating astronomy to the public, and he's an old friend of mine. So I think you'll enjoy it.
There we are. Thank you, Lou. So you've got that to look forward to on Space Oddities next week. Like to thank everybody for being here tonight. I just a couple of things I wanted to pull up, but I can't find them now. Just going back a bit, Michael for Constellation of the Week. Paul says, I've never heard of that constellation, yet as always, there's some interesting objects in it when you look. Absolutely. Thank you for that, Paul. And there was another one I wanted to pull up there somewhere. Can't find it. Anyway, would like to say thank you. Thank you to those of you who donated this evening. Don't forget you can join the Space Oddities Patreon at a very reasonable fee, and you'll find that at patreon.com/Space Oddities, and come and join the community. We want to build a community over there, and it will help you to support us, which is great. And we'll be able to carry on bringing you shows like we have this evening, and possibly even better. So there we are. So thank you for all of us here on the panel. Thank you, Michael. Thank you, Roger. Thank you, Daz. Thank you, Lou, for tonight. And very kind of you to spend your time for our viewers putting this stuff together, as we do every week. So from all of us at Space Oddities, have a fantastic week. We'll be back with Dr. Sten Oldenwald next week as our special guest, and we'll look forward to that very much. And so have a fantastic week, everybody. Thank you for being here, and look after each other. And we'll see you back at 8 p.m. UK time, as always, next week here on Space Oddities. So have a great week. So for more